Let's take a look at this problem. So determine the phase or phases in a system consisting of water at the following conditions and sketch the PV and TV diagrams showing the locations of each of these states. So for case A, the state is defined by pressure and temperature. Then case B, pressure and temperature. Case C, temperature, pressure, D, and E. So I'm going to take one of these cases at a time. And so we're just looking at 2 bar and 120 C. Well, what we can do is make a general sketch of our pressure volume diagram. Again, this is grossly distorted. Then I'm going to just sketch it like that. And likewise, a temperature volume diagram, as I just mentioned, grossly distorted, but there you go. That's typically the way we show it. And you have all of these sequence of states here are saturated vapor states along here, and all of these states in here are saturated liquid, very steep, saturated liquid states. And inside the dome, these are all two-phase. They're two-phase liquid vapor. Okay, that's true for the PV as well as the TV diagrams. Just I should have changed color, made that blue, then change this to red. So right away you know that we have a region of states known as saturated liquid, then the two-phase liquid vapor mixture, and then the saturated vapor states. Well, what about out in this region, which is off to the right? Well, these are superheated. This is all superheated steam, superheated vapor. All right. And then what about this region over here, closer to the axis? These are all liquid states. So a lot of times we'll say it's compressed liquid or subcooled liquid. But the idea is it's liquid. It's not saturated liquid where if I add a little heat to it, it then starts to change phase. It is subcooled liquid. If you add a little heat, the temperature is going to go up, but it's not going to start changing phase. All right. Okay, so there's our PV and TV diagram. So what we want to do is we want to look at 2 bar, 120 degrees, 120.2 degrees C. Well, because they give us a pressure, and it's nice to even pressure of 2 bar, this temperature is not an even temperature. What I would do is I would prefer to go to table A3 instead of table A2 and then make a comparison. And so if we go to table A3, what we're going to be doing is we're going to say, I want to find the saturation temperature for the pressure of 2 bar. And then we'll look that up. And then we'll see, okay, is that saturation temperature at 2 bar equal to this? Then it's somewhere in the two-phase region. Or is it less than that? Well, then it's going to be in the subcooled region. Or if it's greater than that saturation temperature, if 120.2 is greater than saturation temperature, it would be in the superheated region. So we'll go to our table, and we find 2 bar. Got to scroll up just a little bit. Right here is 2 bar. And then we take a look at the saturation temperature. That's that second column right here. It's 120.2. So that allows us, see, so the saturation temperature is 120.2. And so this temperature matches that temperature. It could be anywhere. It could be anywhere on a line of constant pressure of 2 bar from saturated liquid all the way to saturated vapor. Anywhere in there. So it could be, you can't be any more specific than that. It's somewhere in that two-phase region. On a TV diagram, you would come over and you would draw a temperature on the y-axis, 120.2, and you would say it's somewhere between saturated liquid, saturated vapor, somewhere along that horizontal line from the extreme left, saturated liquid, to the extreme right, saturated vapor. Okay, that's the first one. Let's take a look at the second one, and what I'm going to do is go to a clean slide. So we have 2 bar and 120 degrees C. Well, we just said that the Tsat at a pressure of 2 bar comes in at 120.2 degrees C. So you compare this actual temperature, we find the temperature is less than Tsat. Well, it's colder than the saturation temperature, so it's subcooled liquid. All right, so let's resketch our diagram. PV, and we have this dome, okay, and then at 2 bar we had a line of constant temperature where it was 120.2 degrees. It was like this, comes down, hits it, goes across, and goes out. This is a line of constant temperature of 120.2 degrees C. Okay, well, what would a line of constant temperature look like if it was 100 degrees C? Well, it would be come down here, hit, go across, and go out. And this pressure at which it's going to be changing phase is our atmospheric pressure. It's our nearly 1 bar, 1.014 bar pressure. But this line is 100 degrees C. So where is our state? Well, we're on this line of constant temperature, the blue line of 100 degrees C, but we're at a pressure of 2 bar, and the state's at this point right there. So it's 2 bar and 120 degrees C. All right. Now let's go and try and do this on a temperature volume diagram. Go ahead and put in a dome. And what we can do is remind ourselves, hey, we already know that right here is 120.2, and that was changing phase at 2 bar. And so let's go ahead and put in a line of constant pressure. The line of constant pressure of 2 bar looks like that. So you get used to what these lines look like on a PV. You know, it comes down, goes flat, and then goes down again. On a TV, it goes up, goes flat, then goes up again for constant pressure. All right. Now you say, but we're at 2 bar, so we're somewhere on this line, but we're not at 120 degrees C. We're at 100 degrees C, so it's a lower temperature, and there's the state. So there would be the state right there, visually, just kind of where it's at. And so you would say that this state, from the perspective of the temperature, is subcooled. From the perspective of the pressure, it's compressed. But both of them are what we call liquid, L-I-Q, liquid, L-I-Q. Is there really a difference between being subcooled liquid and compressed liquid? It's all on your perspective. Again, if the actual temperature is less than the saturation temperature, you would tend to call it, oh, that's subcooled. That's how you made that deduction. If you take a look at here, the pressure of 2 bar is greater than the saturation pressure of 100 degrees C. So it's compressed, it's higher pressure. Let me just emphasize, what was our saturation pressure at 100? It was 1.014 bar. And so yeah, 2 bar is greater than 1.0. So you would maybe want to describe this as compressed liquid. Again, let me throw some numbers here as a reminder. The saturation temperature is 120.2 degrees C, and our actual temperature was 100. So it was lower. Okay, let's move on to part C. So we have 100 degrees C and 0.5 bar. So right away, that's a special number. That's a boiling point at 1 atm. So we don't even need to go to the table, but we could. We've done that before. Is that the pressure, the saturation pressure at 100 degrees C is 1 atm, or 1.014, because that's the value put in our table, bar. All right, so we can go put a pressure volume diagram, put a temperature specific volume diagram, go ahead and put our dome on, go ahead and put our dome on, and then try to either draw on a pressure volume diagram a line of constant temperature of 100 degrees C. Let's do that. So this one comes down, it's across. This is a line of 100 degrees C, constant temperature. Where does it go into the dome and stay in the dome and go flat, horizontal, at a pressure of 1.014 bar. All right, let's kind of sketch over here on a temperature volume diagram. So what we're going to do is, now let me do this. Let me go ahead and put a line of 1 bar, or 1.014. Here, let me do it that way. It comes up, hits this value, comes across. So if it's at 1.014 bar constant pressure, it changed phase at 100 degrees C. All right. But we're at a pressure of a half of a bar. What does a line of a constant lower constant pressure would be? Something like this. And goes up 0.5 bar. All right. Where is my half a bar? Isn't it down here? 0.5 bar? Sure. So now you say, I know that I'm on a PV diagram, I'm on the red line of 100 degrees C, so I'm somewhere there, I'm at a pressure of 0.5. The only place these two intersect is, and that didn't draw it that well, be like out here. You know, you come across at 0.5 and you're on a line of 100 degrees C. So how do you describe this state out here? It's superheated water. Okay. And then likewise over on TV diagram, you're at 100 degrees C at 0.5. So you draw across and the state is right here. And so it's superheated. So that's how you describe the condition of the water. It's superheated vapor or superheated steam or just even steam. All right. Let's take a look at the next one. So now we have 40 degrees C and 50 bar. Well, this is a huge pressure, isn't it? And so what we would do is we'd think about, okay, you have the pressure volume diagram, and you have the pressure volume diagram, and you put on the pressure up here like this. And actually, I need to be more careful here. Because what is this point up here called? The critical point, right? And so what are the values for that critical point pressure? And what, likewise, this is a TV diagram. We have a dome, bad looking dome, try it again. This is a critical point, and we have the critical point temperature, T critical point, P critical point. Well, if we go to our steam tables, it's either in table A2 or A3, it really doesn't matter. It's the last entry at the very bottom. It's right here. That is our temperature, pressure and temperature of our critical point. That's the highest, it's our peak or of the dome, and above that point you don't have a distinct phase change anymore. It's supercritical. Okay, so if I come back over to my problem, what was this value of temperature? 374 degrees C. And then I forgot, I gotta look back here again. And our pressure, 220, let's round it off, well, 220.9, good enough. So this is 220.9 bar. Okay, that would be 22 megapascal. Okay, so we're sitting down here, good, we're not above the critical point, we're still around 50 bar. Okay, so somewhere we're on this line of 50 bar, and we're on a line here of 40 degrees C, somewhere like there, 40 degrees C. Well, now what we need to do is find a line of constant temperature. If we had a line of constant temperature of 40 degrees C, it would come down, go across, and then kick out. That saturation pressure for 40 degrees C, let's take a look what that shows. Go back up. Go back to table A2. And right here is 40 degrees C. In bar is 0.07384. Just go back, look at the header. I wish I could show the header better, but that's the pressure in bar right here at 40 degrees C, 0.07384. So if we wanted to, you could come over here and say 0.07 whatever 384 bar. Okay. And then here we have 40 degrees C, that's a line going across, but we have a constant pressure of 0.0 blah blah blah. So it would be like coming at a line of constant pressure of 50 bar, right? So the 50 bar, maybe I should go, let me do that. Let me go back to the table. So we find our pressure of 50 bar and ask what is the saturation temperature. So table A3, and 50 bar changes phase at 264 degrees C. All right, so we can put in here, here is 264 degrees C. So our line of constant pressure would be like this, then goes flat, and then goes out, and that's our line of constant pressure of 50 bar. So on both of these, it's where you intersect the 40 degrees C line. I didn't even emphasize that. This is the 40 degrees C isotherm, and 50 bar, so it's right here. So it's compressed liquid. Likewise, the state would be right here on a TV diagram, compressed liquid. Now, one interesting point, because this pressure is so high, we can take a look back at our tables and go all the way back here. And we have properties of compressed liquid water. That's table A5. And because that pressure is so high, we can actually find that pressure and temperature in table A5. I'm not going to do that right now in the interest of time, but you can do that. We don't need to pull out any values, just need to show it on a PV diagram, what it looks like in a TV diagram. And the last one, we have, let me just go to a clean slide, 1 bar and 40 degrees C. So on a PV diagram, put their dome. All right, I'm getting worse at these domes, aren't I? Temperature volume diagram, and we can look at maybe 1 bar right here, 1 bar. All right, and we can think about a line of constant temperature. That line of constant temperature goes down there around, and it's real close to 100 degrees C, because 1 bar is about 1 atm. Okay, and now we're at 40 degrees C. So if I draw another one at a lower temperature, be like this, 40 degrees C, 40 degrees C. At a lower temperature, we would be, hey, subcooled liquid again. All right, take a look at the temperature. So put our TV diagram. Man, I'm getting worse. There you go. And we want to put a line. Well, let's put a 40 degrees C right here, 40 degrees C. And if you had 1 bar, it'd come up, it'd go here, it'd be about 100 degrees C, and then go out. That'd be 1 bar line. And we see, oh, there's the intersection, 40 degrees C at 1 bar, it's subcooled liquid. Well, with that, I hope that helps, and I'm going to go ahead and stop and post this recording.